Our bodies are intricate systems. They rely on a constant supply of oxygen to function. This oxygen is delivered by our blood to every single cell. It is essential for producing energy. Think of it as the fuel that powers our cellular engines. When blood flow to a part of the body is restricted, we call this condition ischemia. This reduction in blood flow means less oxygen gets to the tissues. This creates a state known as hypoxia, which is simply a deficiency of oxygen reaching the cells. This is a serious problem for our health. Without enough oxygen, cells cannot perform their duties properly. Imagine a busy city suddenly having its power supply cut off. Everything grinds to a halt. A similar thing happens inside our bodies during hypoxia. The tiny powerhouses within our cells, called mitochondria, are hit the hardest. Mitochondria use oxygen to generate large amounts of energy through a process called oxidative phosphorylation. When oxygen is scarce, these power plants begin to fail. They can't produce the energy needed to keep the cell healthy and functioning. This cellular stress can trigger a cascade of negative events, leading to cell damage and, in severe cases, cell death. This is not just a temporary issue. Chronic or long-term hypoxia can cause lasting harm. It forces the cells to adapt to a low oxygen environment just to survive. This adaptation might sound like a good thing, but it can have dangerous consequences. The cells start changing how they behave and how they produce energy. This shift is a survival mechanism, but it can pave the way for more serious conditions. Understanding this process is the first step in understanding how something as simple as poor circulation can be linked to complex diseases, including cancer. The link between a lack of oxygen and cellular dysfunction is a critical area of medical research. Scientists have known for a long time that tissues deprived of oxygen become damaged. For instance, a heart attack is caused by ischemia in the heart muscle, and a stroke is caused by ischemia in the brain. But the subtler, long-term effects of mild hypoxia on cellular health are now gaining more attention. It's becoming clear that ensuring good blood flow and oxygenation throughout the body is fundamental to preventing a wide range of health problems and maintaining overall well-being. Nearly a century ago, a brilliant German scientist named Dr. Otto Warburg made a groundbreaking observation. He noticed something peculiar about cancer cells. Even when there was plenty of oxygen available, these cells seemed to prefer a less efficient way of making energy. Instead of using their mitochondria to generate lots of energy with oxygen, they relied heavily on a process called glycolysis. This process takes place in the cell's cytoplasm and produces energy very quickly, but it yields far less fuel. This strange preference for glycolysis, even in the presence of oxygen, became known as the Warburg effect. Dr. Warburg's discovery was revolutionary. At the time, he proposed that this shift in metabolism was the primary cause of cancer. He believed that damage to the mitochondria forced cells to rely on this alternative, more primitive energy pathway. This metabolic change, he argued, was what transformed a normal cell into a cancerous one. While the scientific community today has a more complex view, Warburg's insight laid the foundation for our modern understanding of cancer metabolism. His work earned him the Nobel Prize in Physiology or Medicine in 1931 and opened a new field of study. The Warburg effect is essentially a metabolic signature of many types of cancer. By fermenting glucose into lactate, cancer cells can rapidly produce the building blocks they need to grow and divide. This includes things like nucleotides for DNA replication and lipids for new cell membranes. So, while it's less efficient for pure energy production, this metabolic switch supports the rapid proliferation that is a hallmark of cancer. It's like choosing to build a lot of small, simple shelters quickly, instead of one large, complex building slowly. This unique metabolic strategy gives cancer cells a distinct advantage. It allows them to thrive and outcompete normal cells, even in the challenging, often low-oxygen environment of a growing tumor. The lactate produced as a byproduct also helps to make the surrounding tissue more acidic. This acidic environment can further promote tumor invasion and suppress the body's immune response. Understanding the Warburg effect is not just an academic exercise. It provides a potential target for new cancer therapies aimed at disrupting the fuel supply of these rogue cells. Our understanding of hypoxia's role in cancer took another giant leap forward thanks to the work of Professor Greg Semenza. His research, which also earned a Nobel Prize in 2019, uncovered the molecular switch that cells use to sense and adapt to low oxygen levels. He discovered a protein complex called hypoxia-inducible factor 1, or HIF1. When oxygen levels drop, HIF1 becomes stable and active. It then travels to the cell's nucleus and turns on hundreds of genes that help the cell survive in hypoxic conditions. This is a fundamental survival mechanism for all our cells. Unfortunately, this survival switch can be hijacked by cancer. In many tumors, HIF1 is constantly activated, even when oxygen is present. This is because the tumor environment is often hypoxic due to rapid growth that outpaces the blood supply. The activated HIF1 helps the cancer in several ways. It promotes the Warburg effect, shifting the cell's metabolism to glycolysis. It also stimulates the growth of new blood vessels to feed the tumor, a process called angiogenesis. This helps the cancer to grow, invade nearby tissues, and even spread to other parts of the body. But what can cause this dangerous state of low oxygen in the first place? One emerging area of research points to our own nervous system. Specifically, it involves the sympathetic nervous system, which controls our fight or flight response. When we are under chronic stress, this system can become overactive, a state called chronic sympathetic nerve hyperexcitation. This sustained stress response can cause blood vessels to constrict, reducing blood flow to various tissues throughout the body. This, in turn, can lead to chronic low-grade hypoxia in our cells. This connection between chronic stress, nerve activity, and cellular oxygen levels is a crucial piece of the puzzle. It suggests that our mental and emotional states can have a direct physical impact on our cells, potentially creating an environment where cancer is more likely to develop. If our nerves are constantly telling our blood vessels to tighten up, we are essentially creating a state of self-imposed ischemia. This could trigger the same HIF1 pathway and metabolic shifts, like the Warburg effect, that help cancer cells to thrive, raising our overall risk for the disease over time. The good news is that if factors like chronic stress and poor circulation can contribute to a pro-cancer environment, then we have the power to change them. Making simple, consistent lifestyle changes can have a profound impact on our cellular health. Regular physical activity is one of the most effective tools we have. Exercise helps to improve blood flow, delivering more oxygen to our tissues. It also helps to manage stress, which calms the sympathetic nervous system. A balanced diet, rich in antioxidants and anti-inflammatory foods, can further protect our cells from damage. Managing stress is not a luxury. It is a necessity for long-term health. Practices like meditation, deep breathing exercises, yoga, and even spending time in nature can help shift our nervous system from a fight or flight state to a rest and digest state. This reduces the sympathetic nerve hyperexcitation that can constrict blood vessels. Getting enough quality sleep is also vital, as this is when our body performs most of its repair and recovery functions. By actively managing our stress levels, we can help ensure our cells are getting the oxygen they need to function properly and stay healthy. On the medical front, innovative treatments are being developed that target these very pathways. One such approach is called sympathetic nerve entrapment point injection, or SNEPI. This is a procedure aimed directly at calming overactive sympathetic nerves. By injecting a solution around these nerves, doctors can reduce their hyperexcitation. The goal is to restore normal blood flow and improve oxygenation in the tissues that these nerves control. This could help to reverse the hypoxic conditions that fuel the Warburg effect and support cancer growth, making it a promising strategy for both prevention and treatment. In summary, the journey from a simple lack of oxygen to the complex growth of cancer is a story of cellular survival gone wrong. From Dr. Warburg's initial observations to Professor Semenza's modern discoveries, we now understand how hypoxia and the HIF1 pathway can fuel cancer's fire. By recognizing the role of chronic stress and a hyperactive nervous system in creating these conditions, we are empowered. Through lifestyle improvements and emerging treatments like SNEPI, we can take proactive steps. We can manage our internal environment to deny cancer the low oxygen fuel it needs to grow, promoting our own health and vitality.